right, welcome. This talk is based on my work polishing the OCaml multi-core k-CAS library. It started when Partas asked me to review a couple of his PRs on the library, and I got really interested in it as I have previously implemented prototypes of similar libraries. So I basically took the liberty to work on k-CAS. I don't recall having this much fun programming for a long time, so I hope you'll forgive me for pushing some of my other tasks aside for a moment. Here is a quick overview of what I plan to talk about. First, I want to give a super quick introduction to lock-free programming with CAS or concurrent set as a motivation for k-CAS. Then I'll talk about the new transactional API for programming with k-CAS. After that, I'll describe the k-CAS algorithm that the library is based on. Next, I'll motivate and describe a brand new algorithm for k-CAS and compare based on the earlier algorithm. For the last part, we'll transport to the future. I'll sketch out an idea of how k-CAS could be extended to support blocking transactions and implement STM or composable memory transactions. First, I want to talk a little bit about lock-free programming with CAS. Is it the cowboy coder's dream and the professional programmer's nightmare? But first, what does lock-free actually mean? Is it a cure for all diseases? Well, no. Starvation can be a real issue, for example. Also, lock-free algorithms do not necessarily perform better than algorithms using locks. They can cause just as much or even more contention as they tend to make more, not less, accesses to shared memory. I should also mention that so-called weight-free algorithms also guarantee lack of starvation, but tend to come with a heavier price. Enough with the theory. Let's implement a lock-free stack called the driver stack. Here is a completely standard signature for such a stack. You could implement that signature in many ways. We'll implement it using a single atomic location and concurrent set. The push and try pop demonstrate typical programming patterns using concurrent set. First of all, an atomic get is performed to read the current value of the atomic location. Then an atomic concurrent set is performed to update the location, or attempt such an update. If that fails, a backoff is applied to avoid contention, and the operation is retried. Can you tell what makes this lock-free? Well, assuming that the CPU guarantees that at least one correct CAS succeeds when multiple such operations are attempted simultaneously, then at least one domain will make progress. As simple as the driver stack is, every retry causes costly shared memory traffic. A scalable spin lock, such as the CLH spin lock, may actually generate less shared memory traffic and perform better. The driver stack is perhaps not the best example to demonstrate how subtle it is to program using CAS. As a challenge, you could try to implement an operation to move an element from one stack to another atomically. Good luck. You could probably write a paper on that if you do it in a clever enough way. The truth is that lock-free algorithms using concurrent set are extremely hard to reason about. That is part of why we also have tools to help with that. I should also mention that there are some known gotchas with concurrent set, such as the so-called APA problem, that can bite you, for example, when you are reusing objects. For lack of time, I'm going to skip talking about that. There have been various proposals for extended primitives. For example, one CAS and compares can be used to implement operations on linked data structures such as lists and trees. Perhaps the ultimate primitive would be k-CAS and n-compares, which allows any finite number of locations to be updated atomically, while also requiring any finite number of other locations to remain unchanged during the operation. So recall the challenge about moving an element from one stack to another atomically. Well, with two CAS or double compare and swap, that problem becomes easier. First, we read the values of the two stack locations. Then we construct a list of the CAS operations, attempt to perform them atomically, and finally we retry with backoff as usual in case of failure. But seriously speaking, I mean, the standard computer science solution for this kind of problem is to create an abstraction mechanism. That quote is actually from the paper Parallel Concurrent ML. I mean, of course, you still need the low-level ability to update locations atomically, but indeed, is concurrent set the best programming interface for concurrent programming? And if not, what could be better? I will next introduce one potential abstraction on top of k-CAS. The idea being that instead of writing loops with backoffs, creating and attempting lists of CAS operations, we instead use a transactional API that allows us to read and write shared memory locations, and that constructs the list of operations and retries with backoffs for us automatically. But what is a transaction? Let's first take a peek at the signatures of the core operations on transactions. The snippets on this slide show only the key introduction, elimination, and composition forms for shared memory locations and transactions. So first of all, we can create shared memory locations. We can access them. And in transactions, we can get and set locations. These actually operate on the values during the transaction, and it's possible that the actual locations might be modified during transactions, but the transaction will never see that. Then we can sequence transactions using the return and binding operators. We can attempt a transaction, and if the attempt fails, it will raise an exception. Otherwise, it returns the value of the transaction. Commit does an unconditional commit of the transaction. It just retries the transaction until it succeeds. So logically speaking, a transaction is a composable operation that may read and write shared memory locations and that can be performed atomically by calling commit. Another way to think about transactions is that there are specifications for generating lists of CAS operations against shared memory locations. So here we are just creating a few shared memory locations. Then we are creating a transaction that first reads the A location and gets the A value from it. Then it reads the B location and gets the B value. And then it sets the X location to the difference of the B and A values. That's the transaction. Then we commit the transaction, perform it atomically, and then we can, for example, get the answer. To make programming more convenient and to also allow some optimizations, the library actually provides more than just the minimum number of primitives and combinators. Most of these should be easy to understand in terms of the types and functional programming tradition. In update, the result value is the previous value from the location. The as variants take an additional function that is given the previous value from the location to compute the result. All of the sequencing combinators can be expressed in terms of return and the binding operator. The delay operation is important when side effects, such as allocation of fresh objects, is needed at the start of a transaction. I wish OCaml had special syntax for that. Let's build something real. Here is an entirely traditional sequential stack data structure. It uses a ref to hold a list. Push consists an element to the list. And try pop removes an element, taking it to handle the case of an empty stack. And here is a transactional stack. First, take note of the signature. The push and try pop operations return transactions. The implementation uses shared memory locations. Push is pretty trivial using modify. Try pop is more complex as it needs to handle the case of an empty stack. Note that there are no retry loops or backups. The push and try pop transactions are not significantly more complex than similar code using refs. Here is a more concise implementation of try pop using update as. It makes use of two useful list manipulation functions, adopt and tail save. Aside from being more concise, it's also likely a little bit faster, as this only makes a single access to the internal transaction log. To use the transactional stack, one just needs to call the stack to prepare transactions and then commit them. The commit function takes care of retrying transactions with randomized exponential backoff to avoid contention. You might ask why we didn't just call commit inside push and try pop. We'll come back to that soon. So here we have a log-free queue that fits on a single slide and is pretty much guaranteed to be free of concurrency issues. It uses two shared memory locations for the front and back of the queue. The enqueue operation is just a push to the back. The try to queue operation is more complicated, as it needs to handle several cases. So first, it examines the head or the front of the queue and tries to remove an element from it. If there was actually an element, it returns it. If it was empty, then it examines the back in reverse. And if there was nothing there, well, there's nothing in the queue, it's empty. Otherwise, there was an element in the queue, and then it sets the front to the rest of the elements and returns the first of the reversed elements. But is this queue any good? It can actually perform quite well, as we'll see shortly, but it does have one major weakness. Can you see it? The problem is that reversal of the back might take a long time, and that could cause consumers to starve. As an exercise, you could implement a transactional queue where both operations are constant time and not just in the amortized sense. There is actually nothing new on this slide. It just shows again how to use transactions. But again, why not bake in commit? The reason we didn't bake in commit is that composition of transactions is not limited to primitive transactions. Here is an example of pushing 3 elements to a transactional stack atomically. So one element, second, third, and then we commit. So now we have an operation that pushes 3 elements to a stack. Composition also isn't limited to module abstraction boundaries. Here's an example of moving an element from a transactional stack to a transactional queue atomically. The transaction mechanism makes it trivial to compose independently developed transactions and allows transactional data structures and algorithms to be used for a wider variety of purposes. The transaction abstraction that k-CAS offers seems really nice, but surely it's going to perform poorly. Indeed, what about performance? Is the transaction mechanism a lazy dog and concurrent said the quick brown fox? Well, the mechanism definitely adds overhead, but perhaps not as much as one might expect. This table is based on running a queue benchmark that is part of the regions library. The timings vary between runs, but what's interesting is that the k-CAS transaction-based queues perform quite well. It's actually pretty interesting that the simple 2-stack transactional queue is pretty much competitive with the handwritten log-free Michael-Scott queue. One factor in this is likely that the 2-stack queue probably needs fewer garbage collector and write barriers. Also, a lot of time has been spent tweaking the k-CAS implementation to minimize overheads. Finally, I should note that the transactional node-based queue is just a very straightforward implementation. I would not be surprised if someone came up with a faster one. Next, I'll describe the algorithms used by the k-CAS library internally. While I do not expect you to understand every detail of the algorithms after this talk, I hope to convey a few key ideas and details. k-CAS is based on the JKMZ algorithm published in 2020 that achieves a near optimal k+1 single word CASes per a k-CAS. How is that possible? It's actually a cool trick that's worth understanding. Let me explain. So Fred Brooks has been attributed to saying that, show me your flowcharts and conceal your tables, and I shall continue to be mystified. Show me your tables, and I won't usually need your flowcharts. They'll be obvious. So if you take a moment to think about the data structures or tables used in this algorithm, it should be obvious why the algorithm achieves k+1 cases. So let's take a look. So first, we have a location, which is an atomic reference to a state. A state, it's actually a state descriptor. It holds the both before and after values and a reference to a k-CAS descriptor. The k-CAS descriptor is an atomic reference to status. The status can be either an undetermined list of k-CAS operations, or it can be determined to be after or before. And a single k-CAS is basically a pair of a location and state, with the idea that that location should be updated to hold the new state. And note that there's a difference between these k-CAS descriptors and logical k-CAS operations. These k-CAS descriptors are used internally, and they are basically created by converting logical k-CAS operations to these k-CAS descriptors. So I actually stopped reading the paper on the JK-MZ algorithm as soon as I understood the trick and just implemented it. And of course, I've implemented similar algorithms before, but after just learning about this data structure, I realized that this is how it works. So if you compare the traditional approach, the traditional approach does more work. Can you tell how many k-CASes are needed at minimum? Well, the answer is 2k+1. You will need at least one k-CAS to switch a location to hold a descriptor, and another k-CAS to switch it back to holding a value. And then one more k-CAS is needed to complete the k-CAS operation. JK-MZ avoids the second k-CAS simply by not requiring locations to hold just plain values. With the JK-MZ, the locations may always hold state descriptors. When reading a location, one then needs to check which of the values to read. Note that one of the before or after values is essentially garbage. A real implementation will also need to perform a release operation to avoid the state descriptors from pointing to inaccessible objects. It's a simple detail to take care of after the operation has completed, but we'll skip that for simplicity. As mentioned, to read a location, the operation needs to determine which one of the values before or after to use. The isAfter function, which we'll soon see, does that. The atomically function converts logical k-CAS operations into internal k-CAS descriptors. An important detail is that it creates a cyclic data structure. The cycle is what makes it possible for other domains to get hold of the entire data structure and help to complete an operation initiated by some domain. This is a common pattern in non-blocking algorithms. It might make sense to support LETREC with atomics. This is the core JK-MZ algorithm. It basically just goes through the list of internal descriptors. It compares or checks that the operation is still compares the current value in each location and checks that the operation is still undetermined, and then performs the k-CAS to install the new state to the location. After all the locations have been handled or an inconsistency is detected, it calls finish to attempt to complete the operation. We'll look at finish shortly. Note that isAfter and JK-MZ are mutually recursive. When isAfter is called, it may encounter an undetermined operation. In such a case, it calls JK-MZ in order to complete the operation. This is basically what allows the algorithm to be lock-free. No domain is forced to indefinitely wait for another. By the way, in the beginning, I mentioned that writing lock-free algorithms is subtle business. The three atomic operations in the core algorithm are done in a specific order. What could happen if you change that order? I'll leave that as an exercise. The last part of the algorithm is finish. It attempts the final k-CAS to complete an operation, and then it does one more check to see whether the operation completed successfully or failed. This is also what makes the algorithm atomic. Before the final CAS is performed, no domain may actually read any of the cached locations. The implementation in these slides is, of course, a simplified version. The real implementation uses a splay tree to order the CAS descriptors. Those descriptors are consumed anyway, so the construction of the splay tree is kind of free. And it's also linear time when the logical CASes are already given in some nice order. And the splay tree also functions as the transaction log, and it has the nice property that it optimizes for recently accessed elements. Of course, the real algorithm also has to perform a release step after the final CAS to remove references to unused before or after objects. It also frees the stable CASM descriptors. Also, the implementation has many small tweaks to improve performance. The k-CAS algorithm is nearly optimal for k-CAS. What more could one want? Well, one thing that the k-CAS lacks is efficient read-only compare operations. Next, I'll describe a brand new abstraction tree, k-CAS and a compare algorithm that extends k-CAS. But before we go into the details, here is a motivating example using the transactional API. We have 4 disjoint locations, A, B, X, and Y. We have 2 transactions that both read 2 locations, A and B. One of the transactions then writes to location X, and the other writes to location Y. What happens when the 2 transactions are attempted in parallel? Well, they don't. The algorithm will serialize the operations. To add insult to injury, the CAS also always writes to memory. So even though the A and B locations are not logically modified, they are written to, which causes contention. The way shared memory coherence protocols work is that after a write to memory, only the writer has a copy of that memory location. Assume the above 2 transactions would be done sequentially. The first transaction writes to A and B, which means that A and B are evicted from all the caches except the writer's cache. The second transaction then will have to fetch A and B more expensively and will then write to them and again evict them from all the other caches. This is called cache line ping pong. And this is how it actually looks like inside the CPU. So how could we implement read-only compares? A simple idea would be to just verify that the compares still hold just before performing the final CAS. This sort of post-hoc validation is actually a pretty common pattern in non-blocking algorithms, but it only gives us obstruction freedom, not lock freedom. Recall that lock freedom requires that at least one domain makes progress. Consider a domain performing a compare on X and CAS on Y, and another domain doing a CAS on X and compare on Y. Both may be able to enter the verification step. It's actually a good exercise to figure out how that could happen. And if they both enter the verification step, they would both fail. This could repeat indefinitely, and neither domain could make progress. Okay, let's just see how to change the k-CAS algorithm to give k-CAS and uncompares. The changes are shown as diffs against the reference implementation we saw previously. We modify atomically such that it also accepts compare operations. It then translates those to CAS descriptors without creating a new state. So how can one tell whether a CAS descriptor is a comparison? We just check whether it refers to the CASN of our operation or not. The CASN is always freshly allocated atomically. If the new and old state differ, we check whether we were attempting a read-only compare. If so, then we conclude that the operation failed, because basically it means that the location was modified by someone else. The biggest change to the algorithm is the addition of the post-hoc verification step. Just before attempting to complete the transaction, we go through all the CAS descriptors and check once more that the read-only comparisons are still valid. The actual implementation distinguishes between failure before and during verification. If a transaction attempt fails during verification, then the interference exception is raised. This allows the commit loop to switch to lock-free mode, which only uses k-CAS operations and requires no verification step. This guarantees that with commit, transactions are actually lock-free, so we don't lose anything. Recall the queue implementation. If the queue is empty, the try the queue transaction may only perform read-only comparisons. Also, if the front is empty and the back contains only a single element, the front is not necessarily written. That's because in those cases, the try the queue transaction never writes a new value to those locations. So if you go through the modifications there, the update, the exchange, and the set, then you will see that if the location being modified was already an empty list, then the operation would also write an empty list there. And in that case, it doesn't generate a compare and set, it generates a compare. So the transaction mechanism is smart enough to optimize those cases. This also means that multiple domains can try to dequeue an element from an empty queue in parallel without interference. The conditionals may and not necessarily are there to account for the possibility of interference from writers. So if there's a writer, then of course it can happen that the verification step fails and then the algorithm switches to the lock-free mode. What we have so far is probably about as far as k-CAS can be stretched without adding significant dependencies or overheads. But perhaps we could have a backdoor for an additional feature, blocking transactions. What's that? Consider a transaction that dequeues a value x from QA and enqueues it to QB. Seems straightforward. But what if QA is empty? Should we just keep on retrying in the hope that some other domain pushes an element into QA? That sort of busy wait is usually a poor idea. How might one even implement a dequeue operation that always returns a non-optional value? The idea here is that retry suspends the transaction, waits until some location accessed during the transaction is mutated by some other domain, and then restarts the transaction. This kind of retry is a key idea put forth in the composable memory transactions paper. To support blocking, one essentially needs a way to signal waiters. After mutating some locations, the mutator signals waiters. For a scalable mechanism, that signal needs to be selective and only wake up those waiters that are interested in the mutated locations. To associate waiters with locations in a truly low overhead fashion, one possibility would be to allow locations to be tagged. In a blocking transaction mechanism, that tag could be a bag of the waiters of changes to the location. To make it easy for a blocking transaction mechanism to figure out which locations need to be waited for, limited access to the transaction log could be granted. Reset and retry returns a transaction that resets the current transaction such that it only reads from the accessed locations. The function given to reset and retry is then called with the internal transaction log to construct a transaction that is then composed after the current transaction. The composed transaction is then raised as a retry exception. With written, on the other hand, returns a transaction that executes as the given transaction and then calls the given function with a view of the internal transaction log restricted to the written locations. The return transaction from that function is then composed after the whole transaction. Here is a quick sketch with some blanks left as exercise of how one could implement STM with blocking transactions with the help of tagged locations, reset and retry, and with written. The key point here is the type of blocking STM transactions on the first line. So this is the main idea here. And what this means is that blocking transactions could be implemented with roughly half the performance of plain non-blocking transactions, because we don't have to wrap the transaction, lower level transaction mechanism in any way. And then we actually need to do maybe a double amount of accesses, because we are accessing the waiters lists for each accessed location. So I'm kind of curious to see how well this would perform, and hopefully we'll have this mechanism soon. So in summary, log-free programming with compares and sets is hard. Programming with transactions is easy by composite comparison. Thanks to careful low-level optimizations, the new k-CAS and compare algorithm and inference detection, transactions can give OK performance and log freedom. Transactions give you spread-free concurrency. Thank you for listening. I'm out of slides.